Hello, everybody. Now let's take a look at problem 5.11 from the textbook. So problem 5.11 gives a waveform, and we want to consider that this waveform is the current instead of the voltage, okay? And it's going through a 0.2 millifarad capacitor. All right, and we want to assume instead of this being the peak voltage, like in problem 5.10, let's assume that this is instead the peak current. And we're given the initial voltage on the capacitor as 0 at minus 0.4 seconds. So we're going to determine and plot the voltage. So basically, we're going to cross out this voltage. We're going to say, no, this is actually current in microamps. And let's figure out what the voltage is across a 0.2 millifarad capacitor. So let's break this into parts. Let's look at these different parts, write a piecewise function to describe the current that's going through this capacitor. And then we're going to use that piecewise function to find the voltage. Because remember, if you look in the back of your text at the equations that are there, you can find this function, this equation for the voltage, which is also in the videos, that shows that the voltage is equal to the initial voltage plus 1 over the capacitance, which is this 0.2 millifarad number, integrated from this initial time to the current time of the function it by dt. Now, you'll notice there's these little dt primes, and the reason that they're doing this, right, is because we're engineers, but we want to be mathematically correct. So because we have the time in the integration limits, we're going to say that the function is this dt prime instead of dt. So just so you know what's going on. All right, so if we look at these, we can see, okay, the slope in the first part is 50. So we can write a function 50 times t plus 200 microamps as the current there. Then obviously in 2 and 3, the current is constant at 100 microamps. And then in part 4, we can see that that's just the negative sloping current of the part 1. So we're going to get a 50 times t plus 200 microamps as the current there. All right, so now we have these 4 equations, and 2 and 3 actually, right, they turn out that they're the same. So let's just combine these 2 together. So we have equations to describe the current throughout this time as a piecewise function. Now let's do the integrals. So if I do this integral, I can see that the initial voltage on the capacitor is 0. So this voltage at time t naught, we know that this is 0 volts. So the voltage at time minus 4 seconds is 0 volts. So we can insert these numbers into our equation, right? So we have our initial voltage, we have our function for the current that we already calculated previously in the piecewise function. So now if we go through this problem and work it, we can find a function that describes the voltage. So this function describes the voltage in this first regime or area here. Now, at the very end, we know, so at time t minus 2, right here, so when we transition between these 2 areas, we can see that the voltage is going to be 0.5 volts. So this is going to come up in the next part of the problem. So in the next part of the problem, again, we have this voltage function. And we can see that if we want to calculate the voltage here, we need to know the initial voltage. So good thing we found the initial voltage using the voltage from our regime 1, our area 1 here, which was 0.5. So if we insert our initial voltage and then our function for the current here, we can do this calculation and we can come up with this function, which describes the voltage in the capacitor from minus 2 to 2 in time. All right, great. So we have this function that describes the voltage from here to here. And then let's take a look again, because we know we're gonna need another initial voltage. So we see at time t equals 2, we can see that the voltage is equal to 2.5. So this 2.5 voltage is going to become a new initial voltage for this 4th area. So for the voltage in area 3, we have an initial voltage plus this integral again. And we know again, right, the initial voltage is 2.5. We calculated that in the previous area here. All right, so let's do this integration. And doing the function, we come up with this as the function for voltage. And we can see at the very end here, at time is equal to 4 seconds, that that voltage is going to be 3 volts. And because the current is constant, we can see that the voltage is going to be constant, right? So that's what this is. This is just one little extra area because the current's 0. So if we integrate over 0 amps, we're going to get a constant voltage. So from time equals 4 and beyond, the voltage will remain constant because we could think of the capacitor as being fully charged at this point. Because the current is no longer changing. Okay, so now we have all these areas of voltage. So let's combine them and make a plot. Okay, so let's make a plot now. And so in this plot, we have this function describing the voltage from -4 to 2. And then from 2 to 2, we have this function describing the voltage. And then from 2 to 4, right up to here, we have another function. And then finally, the voltage is going to be constant at 3 volts. So hopefully this gives you an idea of how to use the expressions that we know in order to go from a current in a capacitor to a voltage in a capacitor, basically seeing it charge up or see the voltage change as current in a capacitor changes. And hopefully this also gives you some ideas of how to write these piecewise functions or non-continuous functions. So thank you, and I will see you in the next video.